Welcome to the Stutzman channel. My name is Terry. If you remember, in the last video I replaced an alternator on a 2014 Ford Edge with a 3.5 liter engine. And in this video we're going to go over the technical aspects of how this system works. And we're going to be looking at waveform scanner data, how it works. If you don't have a scope or you don't have a high-end scanner, that's okay. We're going to even cover how you can use a DC voltmeter and has a duty cycle function in it, and you can pretty much diagnose this system. Anyway, there was one person that asked for this video. His name is Master Tech Sarge, and so this video, you might say, will be for you and for anybody else that's interested in the technical parts of it. And by the way, I had my wife look at it, you know, because I haven't completed it yet at this point, so I had her to look it over. She said it was boring, not for her. So like I said, technical videos are not for everybody. You know, I think a lot of people just want to know how to take a part out and put it in, turn the bolts, and they're not so much interested in the technical aspect. But I realize there's a lot of other people out there, you know, technicians and all, that like to know how systems work. And I like to know how they work. So anyway, this video pretty much will be for you. Now, before I started this video, I did more research after I replaced the alternator. So there were some things that I picked up that I did not realize, and I'm going to share that with you too. Now I want to give a shout out to Remy Power Products, because some of the information I got was from them, so I'm giving them credit. And I will put a link to their video for this Ford Smart Charging System about how it works. And you might get some other added info that I may not cover in this video. So, without further ado, let's get started. Ford Smart Charging System, some of the benefits, and this is prevalent across all the manufacturers that's out there. Well, one of the first things that comes up is load management. Now the PCM can take various inputs from the incoming air temperature. It looks at the RPM, vehicle speed sensor. It's got a generator, battery current sensors, and this allows the generator to provide a more accurate current demands for the different modules that's on the cars nowadays. If you remember back in the old days where we had a generator, it had two wires on it, you had one for field, one for a lamp charging indicator light. It pretty much just the charging current was available there all the time, even on startups. And so there was no way that you know, as far as how much charge is going to the battery, how much is going in the load, there was no way that this charging systems was smart back at that time. All right, another thing is load shedding. So the PCM can shut down non-critical loads, such as for the entertainment system, you know, to conserve power for other essential loads. In other words, it may see that the generator is being overloaded, is putting out its maximum current, so you know, it can actually, the PCM can actually shut down some of these loads, you know, to conserve some of this power for other loads that's more critical. Here's a startup mode. Well, when you crank up the engine, as soon as you turn it to the ignition on position, the PCM will recognize that the engine is going to be started. So it's going to send a command out to the generator to say, hey, do not charge, do not put out any current. So there's less load on the crankshaft, on the engine, to allow for faster startups. Longer battery life. Well, the generator can supply more accurate current and voltage control to charge a battery because it has all these extra sensors on here and all this input. So now we're actually looking at the current that's going into the battery. We can see that. We can see how much voltage it is, and we can also see what the actual generator and how much current is putting out. And another thing is better fuel economy. So the PCM can turn the generator off and on, say, while you're cruising down the highway to take the load off the crankshaft. Now, and then in turn, you know, the battery is just sitting there basically not doing nothing. So the generator is supplying all of the electrical current for all the loads. So why not let the battery take care of some of it and give the generator a little break? So once it's got a little break, then, well, that's less load that's on the engine, which is going to give you a little bit better gas mileage. Now, there's two lines that's on this here smart charging system for Ford. One of these lines is called a GENCOM, okay, and that means generator command. So let's look at some of the characteristics on this particular transmission line. Okay, so the PCM will set the desired set point voltage. Now this voltage, if you look on your scanner, the PID is going to be called desired battery voltage. This is the battery voltage set point that's set by the PCM. And it uses a percent duty cycle, which is sent to the regulator, which of course is inside the generator. Now, the higher the percent duty cycle, then the higher the set point voltage. Now, the percent duty cycle has a range from approximately 3% to 95%. Now, here's the thing about this. You would think that the source voltage is coming from the PCM being sent to the regulator, but it's actually the source voltage of the nominal 12 volts. Now, when I say nominal 12 volts, we know that a battery fully charged is 12.66 volts. Now, that's what it will be if the switch is turned to the on position, ignition switch. However, when the engine is running, we know that the battery's voltage is going to be higher. So this voltage is going to vary a little bit. So that's why I say nominal 12 volts. So anyway, this source voltage of 12 volts is sent from the regulator to the PCM, where the PCM will toggle it to ground, and it's creating these square wave pulses for desired percent duty cycle, which equates to this is what the set point voltage is going to be. This is what is telling the generator what set point I want it to be. Now, the command, the PCM command for this will only be present when a new set point voltage is needed. So a lot of times if you look at this here line, say with an oscilloscope, you might see it's 0 volts, and then all of a sudden you see a pulse. Then it might go for 4 or 5 seconds, and then you'll see another pulse. So whenever it needs a new command, you'll see a few of these pulses being generated where it's establishing a new set point. Now the frequency on this line is going to be approximately 125 hertz. Now let's look at the other line. This is the GENMON line. This is line where the regulator inside the generator is sending a duty cycle back to the PCM to let it know what its load characteristics are. All right, so here we go. The regulator provides a feedback to the PCM, and it does it with a percent duty cycle, just similar to the GENCOM line. And it does this to indicate what the generator electrical load is. And this is the amps that's produced by the generator. For example, if we have a low percentage duty cycle, then we're going to have a low generator output, current output. As the duty cycle goes up, then the generator load is going to go up. And that's what we have here. So the higher the percent duty cycle, the higher the generator electrical load. Now the percent duty cycle has a range from approximately 5% to 95%, where on the GENCOM line it was about 3% to 95%, so we can basically say it's pretty much about the same. Now on this one, the source voltage of the nominal 12 volts is sent from the PCM to the regulator, and then the regulator will toggle it off and on to ground, creating square wave pulses for the desired percent duty cycle. And this frequency is approximately 125 hertz on the GENMON line, which is very similar, the same as the GENCOM line. Okay, now let's take a quick look at this here wiring diagram. If you look, you can see that we have all of these here sensors. Here's one generator current sensor. This here is telling the PCM how much current is being produced by the generator, and you can see this on your PID on a scanner. Okay, there's another one that's down here. You see there's another current sensor, and this is looking at the current going in and out of the battery. Now what we are interested in, that we're going to focus on, is those two transmission lines that we talked about. GENCOM, if you look over here, we got GENCOM, and the data is being sent out to the regulator, and I'm indicating that by the blue arrow. And then the regulator is sending out its duty cycle back on the GENMON line, so it's a feedback line. Now, if you look down here, I put this in red just to show that on the GENCOM line, which is right here up on this line here, the regulator is sending out 12 volts, indicated by this red arrow, is sending out 12 volts to the PCM. The PCM is taking that 12 volts and is toggling it to ground, creating a square wave pulses, which is going to be a duty cycle, which in turn is going to be read by the regulator to tell it what kind of voltage it should be putting out. Then in turn, the GENMON line over here in the PCM, the 12 volts is being sent out from the PCM, indicated by this arrow in this direction, sent out in this direction. Then the regulator is going to turn around and it's going to ground that line, and it's going to tell the PCM what electrical load is on the generator. Now here is a chart that I got from a website, and they had a few of the values, but I wasn't satisfied, so I wanted more of these values in here, so I extrapolated the data. Now this is on the GENCOM line. You remember we said that the duty cycle that it creates is to set the point, do a set point voltage. Well, if we look at here, 3%, we can see that right here the set point voltage is pretty much 10.46. The fuel is off, and that is like during a startup, as I mentioned earlier. When the engine is being cranked, it's basically going to tell the generator, hey, don't put out any voltage, current. And so as we can see, as this duty cycle increases, we can see that the set point voltage will increase also. So if we are doing, say, 50% duty cycle on the GENCOM line, we can see that we have 13.82. That you should see inside your scanner. If you have a duty cycle, you can match it up. You can see what your desired set point voltage is, and it should match up pretty much here. Now over here, if you was to take a DC voltmeter and you was to put it on this line, you can read these voltages. And so if you read, let's say using 50% duty cycle, if you see 6.91 volts, then you can pretty much figure that, and you can also figure that that is going to be for a 50% duty cycle. However, if you're going to do this, I would get a voltmeter that can also read duty cycle. Then you can kind of match this thing up to see what it's actually doing. And as I said, as the duty cycle goes up, the voltage increases from the generator. Now, if it gets beyond, say, 95%, then at this point, then we have what's called the error state. And it's going to go into a default regulation. In other words, the generator is going to put out a fixed voltage of 13.8 volts. That is provided that the generator can do it. That is, if the stator is good, the fuel is good, the brushes are good, the diodes are good, and say we have some kind of issue on the communication line, then when it gets past this here 95%, then it's going to put out 13.8 volts. Now, mentioning this is one of the ways that we can also check to see if the alternator will at least put out this voltage. What we can do is we can take the 3-pin line, and we can, as the 3 wires that's going to the generator, remember one of them was GENCOM, one of them was GENSense, and I did not mention the other line, but there's another line right here. And if we follow that, you can see that this is a B+ voltage, goes through a fuse, comes all the way back to the battery. And what that line is always going to be there, this here battery voltage. And this here battery voltage is a sense voltage, which is used in the internal electronics of the regulator. And it's used as a reference point to compare it to, you know, what the generator wants and to what is actually being received here. So anyway, this here 3-pin connector, disconnect it, start the engine, rev it up, and then this generator should, by default, create 13.8 volts. Now if we go to the next slide, we see that it's the GENMON duty cycle, which is representative of the load current that's coming from the generator. And again, you can see that we have our duty cycles going from 3% going down to 95%. And over here, This is what the generator is putting out for current based on what the duty cycle is. Now this is based on 150 amp generator. It's maximum capacity, and this is what was in the 2014 Ford Edge. And as an example, if we're going down here to 50% duty cycle on the GENMON line, we can see that the generator would be putting out 75 amps. And again, you can use your DC voltmeter. You can read this voltage, and then this will equate to what the duty cycle is. And again, it'd be nice to have a voltmeter that can read duty cycle also. Okay, this is a snapshot of a recording of where I was recording the data to get this here generator to fail. Now quickly going over it, this one here is the generator command line fault. Right now we have no error. This is a generator command percent duty cycle. This is telling the generator what the set point voltage is looking for. This here is a generator current sensor output. This is showing how much current is coming out of the generator, showing that the indicator lamp is off with no fault. Here's the generator fault status. Right here we have the generator monitor frequency status, no error. The generator monitor frequency is 126 Hertz. Generator monitor line status, we have no error. Down here we have the generator monitor percent duty cycle, which is 56.42 at the moment, and the desired voltage is looking to be 12.96. So what we're going to do is we're going to go ahead and record it, and then we're going to see the failure of what happens. So I got it set up to play 4 times faster, and it should be coming up here in a little bit. So you can see how the data is changing. You can see how the generator command percent duty cycle is sending pulses to set a new set point. Now right at this point, you can saw there was a little issue there, and now you can see that the generator fault indicator lamp is on, and at this point it never did recover. So you can see we got errors. We got the error on the generator command line fault. You can see right here, let's take a look at the generator monitor frequency. You remember it was at 126 Hertz? Well, this should be reporting all the time what kind of load the generator has or what it's putting out. And you can see that it just dropped. And then at this point, then you can see that the generator command is increasing its percent duty cycle to raise up the set point. So, well, it didn't get no response down here from the generator. So then it starts ratcheting up. So it goes up even higher. So at this point, then it figures, that there is a problem. And so that's where we're at. And you can see we got our error high here, so everything is on high. So we'll just play a little bit more. You can see that the generator current sensor, so you can see now the generator is not putting out any kind of current. It's basically in a dead state right now. And now you can see that pretty much everything is a flat line here. You can see the generator still trying to tell the PCM is still trying to tell the generator here to put some voltage out or current, but the generator is not doing anything. And it continues that way, and it never did recover. Okay, we just saw the scan data. Now all of this data, you saw it was good and then it failed. What I really would love to have is that while I was driving the car, I had the Picoscope hooked up to it so I can get the waveforms, everything is looking good, and then I can see it fail. The only problem was I did capture some waveforms. I did it in the garage, but I had 4 channels hooked up there right there on the alternator. And by the time I got all these probes on there, I'm probably about maybe 3/4 of an inch away from the fan. So if I'm out here driving the car, I got all these probes hooked on there, I was worried that with the engine flexing, the fan come on, and then this one of the probes or more will get caught up in the fan. So I opted not to do that, and that's just why I collected the scan data. But anyway, we do have some Picoscope waveforms where I captured it in the garage, and I got it at startup. We got it when it was just sitting there idling. We turn on the lights, we turn on the AC, we turn on the blower on max, and then we're trying to see how these here pulses will change. So we're going to look at those waveforms. We're going to talk about duty cycle. We're going to talk about how we can calculate it. We're going to look at the frequency. We're going to see how we can calculate it, and then see if we can just get a little bit of knowledge of what these signals will look like under normal conditions. So let's take a look at that now. Okay, this is the Picoscope traces that we were looking at the alternator charging system. Now let's quickly go over the traces and what they are. We got blue, red, green, and a gold or yellow. I've labeled them out down here in the bottom so you can see that channel A, which is the blue trace, this is the B plus stud at the alternator. The red trace, which is channel B, is a B plus sense line at the alternator. Channel C is a green trace, that is the GENCOM line, and channel D is a yellow trace, and that's the GENMON. Okay, now one of the first things, let's take a look and see what is battery voltage that's there on the you know, at the stud that's on the generator. So let me see if I can get that. So about 13.9 maybe. Yeah, they're about 13.9 volts, maybe. Yeah, let's just call it 13.9. Now let's see what's on the sense line. All right, so there on the sense line, we got about 13.54. So you know that's going to be a little bit lower because of the resistance in the wire, because it's going all the way back to the battery too, you know, so it's going to be a little voltage drop. And let's take a look at this here green trace. This is the GENCOM line. You can see that there's going to be some pulses in here. You can see it's at 0 volts. Then it repeats again over here. So let's just take a look. Let's just see what's the interval. How often did this repeat? So we're taking a look over here. All right. So we can see that it's about 5 seconds. Now I should point out that this here trace, these traces were taken right after startup. The engine been running about 30 seconds and I had a lot of load on. So I had the AC on, I had it on maximum, blower, I had the headlights on. So we're looking at the generator is going to probably be putting out a fair amount of current here. Okay, so let's take a look. Let's get a little bit closer look at this here GENCOM, and let's just see what is it doing. Okay, we can see it's generated some pulses, and we can see that we have the GENMON line. We can see the load that's on it. So we're going to focus a little bit more, and we're going to be looking at first thing, we're going to be looking at the duty cycle of this here, the frequency, and we're going to look at the duty cycle and the frequency of the GENMON. Okay, the first thing we want to do, we're going to calculate the duty cycle. Now to do that, we need the width of a pulse. And I'm just going to use this one right here. We're on the green trace. Then I'm going to get another time cursor and just move it a little bit. So the width of this pulse in time is 4.243 milliseconds. Now I'm going to write that down. 4.243 milliseconds. Now I need another time measurement for calculating the duty cycle. Now this is going to be considered up here is going to be our on time. Down here is going to be considered our off time. If you're looking at this on a scanner, the PID, say for GENMON, they're going to be considering that this high state is going to be the percentage of duty cycle. So that's what we're doing, is we're looking at the width of this here pulse when it's high. Okay, so now for the other measurement, we're going to move this over to the start of the next rising edge. So you see how I put the first one on the rising edge of this pulse, and the other cursor is on the rising edge of this pulse. And consider that we're looking at the on time plus the off time. Well, this is called a period, okay? And it is also considered to be one cycle. Now I take a look up here and I can see that my time is 7.924 milliseconds. That's all we need to calculate the duty cycle. So let us go down here. We're going to go to the calculator and we're going to be typing up we want the first one, we want the pulse width. So we want the pulse width first, which is 4.243. We're going to divide that by 7.924. Okay, now this is going to give us a fractional value, but to convert this to a percentage, like with any fraction, decimal fraction, when you want to go to a percentage, you will always multiply it times 100. And you can see that that gives us 53.5% duty cycle. Okay, going back and looking at this 53.5% duty cycle, looking back at my table, this is about 13.9 volts. Now, as a quick refresher, let's go back and let's just see what our battery voltage is. And look, you can see 13.9 volts, so that turned out pretty good right there. Okay? Now, at this point right now, we need to prove, let's just prove that our calculation on our duty cycle, was correct. So let's go back and we're going to add a measurement. All right, we got this here green trace. That's what we're looking at. We're looking at the duty cycle. All right, we're looking between the rulers and let's see what we get. And look at here, 53.42. I came up with 53.5% duty cycle. So that looks pretty darn good. Now, while we have the cursors right here on the measuring the period, let's go for the frequency. So to do the frequency, to calculate it, I'm going to bring the calculator up. Now, the first thing I'm going to type in is 1. Why 1? Because 1 is for 1 second. What we're looking at is frequency is measured in hertz, which is basically saying, how many of these cycles can we do in 1 second? Well, obviously, this is not 1 second. It's only 7.924 milliseconds. So what we're going to do is we're going to convert this to see how many of these cycles can we do in 1 second. Remember, frequency is always measured in 1 second. How many cycles can you do? So, but we have to take this here measurement of 7.924 milliseconds. We have to convert it to seconds because we got 1 second on top, which we're going to divide by this time measurement. So we need to convert this to seconds. So we're going to say 1 divided by, and we're going to take the decimal point, we're going to shift it 3 places to the left, and that will convert this milliseconds into seconds. So that will be 0.007924, and now enter, and look at there. We got 126.2 hertz. All right, and you remember earlier in the video that we said that this here GENMON line should be about 125 hertz. Looks pretty good to me. All right, now let's confirm it. Let's see what the measurement says from Picoscope. So if my cursor is exactly where they are, looking at period, we're going to measure frequency. We're going to look at it between the rulers. And look, 126.6 hertz. I came up with 126.1, and that was very close. All right, now let's take a look, get a little closer look at this one down here. Let's take a look at the GENMON line. Now we're going to do exactly the same thing. I'm going to start right here on the rising edge of this here pulse, this one right here. I want to see how wide is that pulse. What's the time period on it? So I can see that the pulse width is 7.648 milliseconds. Now to get the period of this here, which is 1 cycle, remember that includes the on time plus the off time. and I have 7.936 milliseconds. All right, let's do our calculation. So we have 7.648 divided by 7.936. Remember to go to percent times 100. And you can see that we have 96.3%. 96.3% duty cycle. Well, that shows you right there that this here generator is putting out a fair amount of current. Because you remember I said that I just cranked it up and I turned on the loads as far as the AC. I had the blower wide open. I had the headlights on. So this thing is putting out some current. Now, this 96%, what is the rated amount of current that it's putting out? Remember, this here generator has 150 amp capacity. So how much current is it putting out? We say 150, that's the maximum amount of the capacity of the generator, times 0.96. And this generator is putting out 144 amps. That is pretty wild. All right. Now, let's take another look at another thing here. And this is going to be like the startup. So let's go over to another waveform or another buffer. If you look right over in here, in this area to the right of your screen, you can see here's my battery voltage that's at the alternator. You can see it dropped. Well, this is right in here is where I started the engine. Okay, so let's take a closer look at that. See what's going on there. So I'll just come right down in here. Okay. Okay, notice right in here, this is where I turned the ignition on and started the engine up. But look at the GENMON line. Do you notice how it has very narrow pulses here? And look down here. Notice how the generator is not doing anything. It's flat as zero. It's not giving me any duty cycle, which means that it's not putting out any kind of current at all. So basically the generator is turned off because we're in a startup condition. But let's take a quick look here. Let's just kind of zoom in on this right here and see what kind of duty cycle we have. Okay, so we're going to come in here. We want to get our pulse width, right? And we have a pulse width of 253.9 microseconds. All right, now let's see what is our time period. So rising edge to rising edge, we have 8.005 milliseconds. Now remember, in duty cycle, your time units has to be the same. It could be microseconds, you know, for both values, or it could be milliseconds, seconds, but they got to be the same. Now remember, the first one was in microseconds, right? So I have to convert that value. I'm going to convert this value right here, which I had originally was 253.9. All right. Well, I'm just going to go ahead and I'm going to use our new value, whatever I come up with. And that looks pretty close to me. So we got 253.9, so I got it right back to where it was at. So to convert this into milliseconds, which will be the same time period as I was for my period, remember, I need to shift the decimal point 3 places to the left, and that will give me milliseconds. All right, so let's go ahead and let's get our calculator up. So we type in 0.2539, that's in the milliseconds, divided by 8.005 milliseconds times 100. And look at there, 3%. You remember earlier we talked about the 3% that at startup. This is what your duty cycle is for the, at startup. So basically the generator is telling the PCM is telling the generator, just basically turn off, don't have any current, don't put out any current, so we can have faster startups. All right. Okay, so that looked pretty good. Now let me get it back to our period. All right, right there. And now if we want to see what his measurement is, just to confirm it, always want to confirm, right? Again, we're on C. We're looking at duty cycle between the rulers. And we look down here, you can see we got 3.2% duty cycle. That looks pretty good. Now while we have it right here, let us see what is our frequency. Should be around about 125 hertz, right? Well, let's confirm it. So we're going to go back to our calculator. Remember, we're going to type in 1 divided. Now this is our time period. That's what we want. But we have to convert milliseconds to seconds. So this is going to be 0.008013. And look at there, 124.7. That is very, very close to 125. Okay? Looks good. Looks very good. And let's see, was there anything else that we can cover here? Okay. Yeah, let's confirm my measurement. So let's go to C. We're looking at frequency between the rulers. And look at that. It came right dead on the money. 125 hertz. Can't get no better than that. Wow. And that's pretty good. So anyway, that gives you an idea, kind of see what's going on with these here pulses. So hope you learned something, and catch you in the next shot here. Now, wasn't that the coolest thing that you ever did see? Where the system of how it's supposed to work and it matches right up with the data? So I thought it was pretty good. There was one thing that I forgot to mention in the video, so I'll put it here in the closing. When you're diagnosing this system, you know that I mentioned about you can unplug the 3-wire connector from the generator, rev the engine, and then the generator should go into a default mode where it should put out 13.8 volts fixed. Okay, but what about the computer? What about the COM line, the GENCOM line, and the GENMON line? Well, what you can do is you can take a jumper with the connector unplugged, put a jumper between the GENCOM and the GENMON line. Now what that will do, of course you got the engine on, or it can be running, and you want to have your scanner, and you want to be looking at the GENCOM, say, percent duty cycle, and your GENMON percent duty cycle. And what that would do is that the PCM will send a signal out, and it will route right back into the GENCOM, so it'll see the 12 volts. And what it will do is the GENCOM will send out a signal, right, a pulse duty cycle, and then it will turn around and go right back into the other one, you know, as far as the GENMON. Well, then the GENMON is going to be doing what it's doing, and then the generator command is going to shut down because it's equal to a set point. And what will happen is then you will see the PIDs, and they will go back to 0, and then you will see the GENCOM go to 0. Well, then the GENCOM is going to say, wait a minute, he's not reporting back, you know, because it's not reporting back what the load is on the generator. So then it's going to turn around and start talking back to it again. So you'll see these PIDs, they'll go on, and then the other one will come on, and then they'll fall back down. So you'll see them alternating. Once you see that, you know that those lines, both of these lines here are okay, and you know that the PC is okay, PCM is okay, because it's doing this, the algorithm is doing what it's supposed to do. So that's another check that you can do to check your system there. So anyway, I hope you learned something. Hope it can help you in diagnosing these forward charging systems, and we'll see you guys in the next one. Oh, and one other thing. You know what this means? It means now you know everything that I know about this system. So you guys take care. We'll see you in the next one.